let me tell you one thing. There are two categories of algorithms. There are two categories of sorting algorithms. First category is comparison based sorting algorithms. Okay. And second category is non-comparison based sorting algorithms. Okay. Comparison based sorting algorithms means such kind of sorting algorithms in which comparison is indispensable. Okay. Indispensable means you have to do comparison. You cannot let go of comparison. So whatever code you will be writing for such algorithms, you have to write these kinds of things. Comparators and all these things have to come. So tell me, the sorting algorithms that you have mentioned just now, not in fact just now, but which you were mentioning before, which were bubble sort, merge sort, or heap sort, in which categories do they lie? Do they lie in comparison based or do they lie in non-comparison based? They must lie in comparison based, because in bubble sort you compare, in selection sort you compare, in merge sort also you compare. Okay, in all of those sorting algorithms you compare, right? So all of them are comparison based sorting algorithms. Now let's think of one thing, that if let's say there are n elements which are supposed to be sorted, then how much time does it take to compare two numbers? Can I assume it to be order 1? Order 1, right? So how many comparisons will be there? If there are n elements, then what is the maximum number of comparisons that I can have? N is not the right answer. When you compare a pair. So it indirectly means to say that how many pairs can you think of? So think of it in the worst case. In the worst case, how many comparisons you have to do in bubble sort or any other sorting algorithm? That is n into n minus 1 by 2, right? Because how many different pairs you can have? If you have got n different elements, then you can have n C2 different pairs, right? Which is n into n minus 1 by 2. So an upper bound on the time complexity of comparison based sorting algorithm will be n square. That in the worst case, you will end up doing n square comparisons, and only then you will be able to position elements at their respective places. So this is an upper bound on comparison based sorting algorithm. Upper bound means that whatever comparison based algorithm you might know would take this much time, n square, order n square time, and it should not take more than n square time. I mean, if you are thinking any n cube sorting algorithm, then maybe you are doing some redundant work in that. Okay, n square is okay. N square is the most naive, and anything which is n cube or n raised to power 4 is simply stupid. Okay. Okay. Now, what can be the lower bound on this? Can you think of the fastest comparison based algorithm? Order n, you can never sort an array in order n time using comparison logics. You have to do something else over there. Okay. So that is n log n over here. Like for example, merge sort and quick sort. Do not worry if you don't know this. I'm just taking the names because these are popular. I will be teaching them in detail. Okay. So n log n is the best amount of time, or n log n is the minimum number of comparison operations that you have to do. Okay, you cannot get your job done in something lesser than this. And how, that we'll learn over there. Okay, so there is a very beautiful technique which lets us reduce this n square to n log n, and we'll all visualize that. Okay, so the point is this, that if comparison is to be done, then you cannot do better than this. Then there is another category of sorting algorithms, non-comparison based, which doesn't use these things, which doesn't need to compare an element with the other element. Okay, so when I write this, that means you are comparing an element of the array with other element of the array. So these algorithms do not perform comparison at all. So sometimes they are linear, sometimes, this is very important, not always, sometimes they are linear. Linear means order n, but in other times they are very, very bad. In fact, they are worst. Okay, and we'll understand those at later point of time. Cool. So let us start our journey with these kind of guys. Okay, we'll start our journey with comparison based sorting algorithm. So I'm going to remove this. Okay, so let us pick one comparison based algorithm and let us understand how it works and everything. Okay, so maybe let us pick something like insertion sort. Okay, so what does insertion sort mean? The most important word over here is this itself, insert. Okay, So what does it do? It does very simple thing. It simply inserts a new element, let's say x. It simply inserts a new element x at its deserving position in an already sorted sequence. This is very important. So it inserts a new element at its deserving position in an already sorted sequence. Okay, so let us just try to do this. Let's say there is an already sorted sequence like 5, 7, 11, 23 and 45, and then there comes a number which is 9, which is a new element. Okay, this is sorted, okay, and let's say the size of this is n. My first question to you is, how much time will you take to decide that which index is the deserving index for this in this array? How much time will you take to do that? Just focus on my question. You just have to decide the deserving index for this. Okay, think again. I'm not asking you to put it at that index. I'm just asking you to tell me the deserving index of this in this given sorted array. Can you do that in login? Yes. Because this is sorted, so in binary search you can figure that out. Yes, no guys? I think there was a question also like this in your binary search assignment, right? So you can easily figure out what should be the deserving index of new incoming element. Now, figuring out that index and placing the element at that index are two entirely different things. Okay, so you can figure that out very easily, but when it comes about placing it, then what you have to do? Then in worst case you can take order n time. Why? Because this is an array. An array is a contiguous data structure, so there is no vacancy between 9 is to be positioned here, okay, which is the index of 11. So there is no vacancy between these two. That means that if it has to come over here, that would result in this moving here, this moving here, and this moving here. In the worst case, what could happen is that this could have been a number like 0, which you were supposed to place over here, and that would have required to move everything towards their right by 1 unit. So how much time would it have taken? So let's say had it been a number that would have been smaller than the smallest, in that case how much time would it have taken? So let's say you determined that this is the deserving index. For that you took log n time, okay, and then in order to put it over here you are moving everything right by 1 unit, right? So order n time for that. Order n plus log n would have been order n. So in order n time you are able to do this thing. A new element comes and I already have a sorted array, and then I position that new element at its deserving location in the sorted array such that the resultant array is also sorted. So that particular operation will take me order n time, where n was the size of array. Okay, cool. Now one thing is very clear to understand, that binary search is an overkill over here. Why? Because the second step is anyways going to take me order n time. So why use binary search to figure out that at which index it should come? Although you can do that, but it is not very necessary to do that. Okay, right? Because the second step would anyway take order n time. So the easiest way to deal with these things could be, let's say a new element called as 15 comes. Okay, so what you can do is, so let's say it is a big array, many elements are yet to come, the array is waiting for it, and the new element that has come is 15. So you can first position this 15 over here, and now what you can do is that you can just, because this is sorted, so you can just compare this with the last element, and if the last element is greater, then you will swap. So when you swap, what is going to happen? When you swap, you will have a 45 here and you will have a 15 here. Now you will compare this with its previous element. This is also greater. So again you will swap this and this. So now what will happen? You will have a 23 over here and you will have a 15 over here. Again you will compare this and this. What will you do at this point of time? At this point of the time you will happen to see that this 15 is greater than this 11. Since this 15 is greater than this 11 and the array was sorted, so can I comment that everything in the back of 11 would also be smaller than 15, right? So what I can do is I can simply let 15 stay over here. So what actually happened, that this slot has 15 now, this slot has 23 now, and this slot has 45 now. So this is the way you are actually solving the problem. So you had a sorted array like 5, 9, 15, 22, and something new came like 6. So you compare this with this, okay, and if this is greater, you swap, okay, and then you get 6, 22. And then you do the same thing at this level. You compare this with this. If it is greater, you swap. Then you get 16, 6, and then 15. Again, you compare this with this. It is greater, swap. You get 6, and this is 9. You try to do the same thing over here, and you see that swapping is not required, so you terminate over here. So these operations that you have done, it can happen at max order n times. Okay. Okay, you have to be careful about one thing. And what is that one thing that you have to be careful about? Let's say that element was very small. Let's say that element was like 3. So it would have, crawled till here, isn't it? It would have crawled till here and pushed everything else 1 unit towards, right? Here number of checks are greater than binary search, right? Not exactly, because while you are trying to position the element at its deserving location, in that step you have to do these things that I am doing anyways. I mean, you have to put one element at I-1 and other element at index I. So it doesn't really make a difference. So whatever I am doing over here, that you would anyways do over there also, okay, after you have found out the index. Yeah, so what I was saying was, let's say the element has successfully come over here. Now you must not compare AI and AI minus 1. Are you getting it right? Because for I equals to 0, AI minus 1 will lend you index out of bound exception. So you should be very sure that if you have already reached index 0, if you have positioned your new element at index 0 by crawling it from I minus 1 to 0, then you should simply stop over there. Okay, so now let us try to write the code for it. Okay, see, the requirement of insertion sort to start working is that there should be an initially sorted sequence. So let's say an array was given to you like this. Okay, so there should be an initially sorted sequence. So can you think of a subarray? Let me not use the word sequence because that is discrete. Can you think of a subarray of this array which is already sorted? Yeah. If I consider just this much of subarray, then this is already sorted, right? And then I can regard this element as a new element and then try to position this in this such that the resultant looks sorted. So that I can do. I'll compare 1 with 7 and then 1 will come over here and 7 will come over here. Now see, this much of part is sorted now, right? Now you will consider this element as your new element. Now you will start these kind of things. So you will compare 5 with 7, it is smaller, so 5 comes here, 7 comes here. 5 and 7, 5 is already greater, so no need of doing that, okay? So you can stop over here, right? Now this will be your new element. Again, you will compare 6 with 7, 6 is smaller, so 6 comes here, 7 comes here. Comparing 6 with 5 tells you that, hey, this is already greater, so no need of going back, okay? So now again, till here it is sorted. Now you come here, okay? So now you will compare this 3 with 7, you will find that this 3 is smaller, so 3 comes here, 7 comes here. Then you will compare 3 with 6, again there is a need to swap. Again there is a need to swap. Now there is no need to swap. So now this has been completely sorted. So this is how insertion sort works its way around, that it first considers that, hey, everything from index 0 to 0 is sorted. So now I'll make everything from index 0 to 1 sorted. And how? By considering a of 1 as my new element. After I am done with that, then I'll move on to a of 2. Then I'll move to a of 3 and eventually I'll move to a of n minus 1. Okay. Okay, at this point of time, just try to tell me one thing. I'm going to be very specific and you also be very specific, okay? So let's say this was your index I, okay? This was your ith element. What could have been the maximum time taken to place it at its deserving location in the initially sorted array? If its index was I, what could have been the maximum time required to place it at its deserving position in the initially sorted array, right? So that should be the answer, because I simply asked that what will be the maximum number of, see, each of these operations that you are doing can be thought of as order 1 operation. So in the worst case where this is smaller than this also, you will crawl your way from I till 0. So for this ith element, in the worst case, you will take order I time. Okay. Let us consider, no, let us not consider anything. So what could be the worst case time complexity of this entire algorithm? Can you think of the worst case time complexity of it? So for the first element, you will have 0 operations. For this element, 1 operations. For this element, in the worst case, 2 operations. For this, 3, and so on. For the last element, n minus 1 operations, almost n minus 1 operations, and the sum of this is going to be n minus 1 by 2. So it will be order n square in the worst case. So this is how the time complexity will look like. Now let me ask you a question. If let's say the array was sorted, so let's say you had an array like this, what would have been the time complexity of insertion sort for this? It would have been order n. Why? Because here you would have immediately compared and said that no need to swap and go back. Just one comparison. Here also just one comparison. Here also just one comparison. So at every level, at every element there is just one comparison, and there are n elements, so it will just be order n. So if the array is extremely sorted, I mean if the array is totally sorted, then the time complexity will be order n. And when would the maximum number of operations happen? When the array is completely sorted in descending order, right? If it is sorted in descending order, then it naturally makes sense of having that done. So let's say you have something like this. So this can have maximum of 1 swaps, and that will happen. Okay, now let's say this has become 4, 5, but this was sorted in descending, so this is smaller than both of these. Okay, so the number of swap operations will be equal to 2. And then for this 1 will be gone on till the end. So if it is sorted in descending order, then it will take order n square time. So there is an important lesson to take from here. The time complexity of insertion sort is dependent upon the extent to which your array is sorted. If it is sorted completely in your favor, which is sorted in ascending order, then you are very happy, and if it is just reverse of you, then you are very sad. Is it clear to everyone? Does that make sense to all? This was a very important point, by the way, right? That the extent to which array is sorted, that would determine the runtime of it. And now the extent to which an array is sorted, this can be denoted by a mathematical number, and we will discuss it in time to come. So that number will tell that, hey, if that number is high, then the array is very much unsorted, and if that number is low, then the array is unsorted but very less unsorted. Okay, so yeah, let us move down. If let's say I have to write the code of the insertion sort, so what happens? I take it for granted that the portion from 0 to 0 is initially sorted, okay, and then I start my journey from this index. So I'll start my journey from index I, and all the way I'll go to n minus 1. Okay, now the moment you pick an element, now you need to start your series of comparisons with the backward elements and swaps. Compare, swap, compare, swap. The moment you see that compare did not result in a swap, so you can terminate. Okay, you can terminate that particular nested loop which is going to come within this for loop, right? So for that, let me do one thing. I'm going to take j equals to I, and now I'll write while. So you compare an element with the neighbor, which is the left neighbor, right? So you compare while aj is smaller than aj minus 1. Okay, till that time what you are doing? You are doing swap of aj comma aj minus 1, and after making this swap, then you go to the next element, which is next previous element. So let's say if you swap this minus 1 and 0, okay, now you will try to compare minus 1 and this. So for that, your j should be decremented. Okay, okay, is this code safe, or is there a condition that I am missing? Yeah, what if I reached 0th index? If I reached 0th index, if my j became 0, then j minus 1 will result in index out of bound exception. Guys, are you all getting this point? Yes or no? So I need to add one more condition over here, and that condition should be that while my j is positive, and this, then only I'll come over here. And the nature of AND operator is that if this is false, then this will never be evaluated and immediately the loop would be broken. So this is how my job would get done, and this is the code, simple code for insertion sort. Okay, great. Now take a look at this and tell me whether this insertion sort, is it a stable sorting algorithm or is it unstable? So let us take that by an example. So let's say you had something like 4, 1, and then let's say you again had 1 and then you had others. Okay, so let's say this was your first occurrence of 1, this was your second occurrence of 1. So what is this algorithm doing? Okay, see, the condition which is over here is that condition says that, hey, if this jth element, let's say there was an element here, if this jth element is strictly smaller than your left neighbor, then only you perform that swap. If there is an equality, then swap will not be performed. Okay, did you get this point? Yes, no? If you got this point, are you able to now decide on your own whether it should be stable or unstable? So what would initially happen? Here there is no point of stability because here the elements are different, so the swap is indispensable. So 1 will come over here and 4 will come over here. Now when you are over here, so now first you will compare this and this, so swap has to happen. So this 1 comes here and this 4 comes here. Now when you are comparing these and these, what would happen? Will this while condition be true or false? It will be false because this element is not greater than this element, this is equal to this element, so the swap operation would not happen and everything is alright for me. This was the first occurrence of 1 which has come first and second occurrence of 1 that has come second, right? So because of this kind of condition, this thing that you have, this thing is called as comparator. So within every sorting algorithm there is a comparator, and this is the comparator of insertion sort. Because of this comparator, this insertion sort is being called as stable sorting algorithm. Okay, but what if I change it to this? So let's do it piece by piece. If I change it to this, will my output array become unsorted? Will it become unsorted? Yes, no? No. But what will go wrong? It will become unstable, and it will become highly unstable because now the first occurrence would come at the last position and last occurrence would go all the way back to the first position. Keep one thing in your mind. If anyone asks you a question that, hey, if XYZ algorithm is stable or unstable, that question is a vague question. Why that is vague? Because it totally depends upon the comparator that you have written. Okay. Same sorting algorithm with one kind of comparator can be stable, but if you change the comparator, it can become unstable. Okay, right? So this is one thing that you have to always keep in your mind.